Hi, I am Pradosh Kumar, working as an assistant professor in the Department of Biomedical Engineering, Sri Shanmuga College of India and Technology. In this session, I am going to discuss about PN junction diode. First, we should know about the N-type material and P-type material that will contribute to form a PN junction diode. First, we will discuss about N-type material. When extra valence electrons are introduced into a material such as silicon, and N-type material is produced. The extra valence electrons are introduced by putting impurities or dopant into the silicon. The dopant used to create an N-type material are group 5 elements. The most commonly used dopant from group 5 elements are arsenic, antimony and phosphorus. The diagram which is shown on the left side shows the extra electron that will be present when a group 5 dopant is introduced to a material such as silicon. This extra electron is very mobile. Next we will discuss about the p-type material. P-type material is produced when the dopant that is introduced is from group 3. Group 3 elements have only 3 valence electrons and therefore there is an electron missing. This missing creates a hole or a positively charged that can move around in the material. Commonly used group 3 dopant are aluminum, boron and gallium. The diagram to the left shows the hole that will be present when a group 3 dopant is introduced to a material such as silicon. The PN junction. The PN junction is formed by adding P-type material and N-type material. In steady-state case, when no extra source is connected to the PN junction, diffusion and drift balance each other out for both the holes and electrons. Space charge region. It is also called as depletion region. This region includes the net positively and negatively charged regions. The space charge region does not have any free carriers. It is called as depletion region since it is depleted of charge carriers. Metallurgical junction. The interface where the p-type and n-type materials meet is nothing but a metallurgical junction. So this PN junction, we have to bias this PN junction in order to reduce the width of the depletion region for making the device to conduct. So next we will discuss about the biased PN junction. The PN junction is considered to be biased when an external voltage is applied to PN junction. There are two types of biasing available, forward bias and reverse bias. In this figure, a biased circuit is shown, that is PN junction connected to a bias, that is we can say this like a forward bias. Forward biased PN junction. Forward biased PN junction means applied voltage which will be greater than 0. In forward bias, the depletion region shrinks slightly in width. With this shrinking, the energy required for charge carriers to cross the depletion region decreases exponentially. Therefore, as the applied voltage increases, current starts to flow across the junction. The barrier potential of the diode is the voltage at which appreciable current starts to flow through the diode. The barrier potential varies for different materials. This is called forward bias because a p-type that is a positive of the battery is connected to the p-type material and a negative terminal of battery is connected to the n-type material. So it is called as the forward biased junction. So here, due to the forward biasing, the width of the depletion region will decrease, which will result in the flow of current. So the circuit which is shown on the right side, which shows the PN junction diode is connected through a current limiting resistor, and we have given the forward bias to the circuit. The below circuit shows that the diode which work as a short circuit, that is it will work since it will conduct due to the forward bias applied. The forward characteristic curve for a PN junction diode. The application of forward bias voltage on the junction diode results in the depletion layer become very thin and narrow, which represents a low impedance path through the junction, thereby allowing high current to flow. The point at which a sudden increase in current takes place is represented on the static IV characteristics curve, which is known as the knee point. That is the voltage at which the current start to increase and the voltage become constant. That we used to call as the knee voltage, which occurs in the forward bias. For a silicon, the conduction occurs at 0.7 volt. Suppose if the material we are using is germanium, means the conduction will occur at 0.3 volt. Reverse biased PN junction. When a diode is connected in a reverse biased condition, that is, a positive voltage is applied to the n-type material and a negative voltage is applied to the p-type material, which is shown in the figure below. The positive voltage applied to the n-type material attracts electrons towards the positive electrode and away from the junction, while the holes in the p-type end are also attracted away from the junction towards the negative electrode. The net result is the depletion layer grows wider due to lack of electrons and holes and presents a high impedance path almost like insulator. The result is that a high potential barrier is created, thus preventing current from flowing through the semiconductor material. A small leakage current, which is called a saturation current, flows under a reverse bias condition. This saturation current is made up of electron-hole pairs being produced in the depletion region. Here we can show the figure of the circuit where a PN junction diode is connected in the reverse bias junction. A resistor is connected to avoid the overflow affecting the diode. So the below diagram which shows like an open circuit means that during reverse bias junction the circuit behaves like an open circuit. Reverse characteristic curve for a PN junction diode. Sometimes this avalanche effect has practical application in voltage stabilizing circuits where a series limiting resistor is used with the diode to limit the reverse breakdown to a preset maximum value, thereby producing a fixed voltage output across the diode. These types of diodes are commonly known as Zener diodes. Where we can see in a Zener diode, suppose a Zener diode with specification of 6.2 Zener means then a breakdown will occur at 6.2 voltage where the current will increase and the voltage will remain constant. Hence we used to call the Zener diode as a voltage regulator. Types of diodes and their uses. PN junction diodes are used to allow current to flow in one direction while blocking current flow in the opposite direction. The PN junction diode is a typical diode that has been used in previous circuits. We have shown the symbol of a PN junction diode. Next is the Zener diodes. These are specifically designed to operate under reverse breakdown condition. These diodes have an accurate and specific reverse breakdown voltage. And the next one is the light emitting diode. Light emitting diodes are designed with a very large band gap. So movement of carriers across the depletion region emits photons of light energy. Lower band gap LEDs emit infrared radiation, while LED with higher band gap energy emit visible light. Many stoplights are now starting to use LEDs because they are extremely bright and last longer than regular bulbs for a relatively low cost. So this is a symbol of a light emitting diode. We can see the diode like a PN junction diode, and the arrow indicates that a light emits. This is a photodiode. While LEDs emit light, photodiodes are sensitive to received light. They are constructed so their PN junction can be exposed to the outside through a clear window or a lens. In photoconductive mode, the saturation current increases in proportion to the intensity of the received light. This type of diode is used in CD players. In photovoltaic mode, when the PN junction is exposed to a certain wavelength of light, the diode generates voltage and can be used as an energy source. This type of diode is used in the production of solar power. Okay, thank you for listening to me to my session. Thank you.